Hello, I welcome you all in this presentation related to the subject materials processing fundamentals and practical. And we are talking about the welding of the metals. And in this presentation also I will be talking about the few fundamentals related with the welding of the metals. So this presentation includes like the typical fusion weld joints or the joints developed by the solid state joining process or other joining processes. What are the important factors that affect the joint performance? Then what is the importance or the role of the heat, pressure and the filler metal in the welding? And what are the common heat sources which are used for the welding, like the combustion of the fuel gas and oxygen mixture, arc, or your the laser electron beam, like that. Then how the power density of the heat source and the heat input are related with each other, because this affects the weld joint characteristics significantly. So how the heat input affects the weld joint performance, and additionally when the fusion welding is carried out or the heat generated during the welding is high, significant increase in temperature of the parent metal leads to the interaction of the metal with the atmospheric gases. So we that contaminates the weld joints and degrades the quality of the weld joints. Therefore it is important to protect the weld pool. Okay. So weld joint can be developed, like say, simply by melting the fine surfaces of the base metals and permitting it to solidify in case of the autogeneous welding. This kind of the approach is good when we are welding the thin sheets, or the base metals or the parent metals to be welded almost same, or they are perfectly compatible with each other. So, these are the two cases, same base metal or they are compatible with each other when they are brought in the molten condition. Under those conditions, autogeneous welding is considered to be fine. But if the section thickness is high, then we need to prepare the edges, okay, like this. And then this the gap between the parent metals A and B which is created needs to be filled in. So we need the external filler metal to fill this. Okay, this is one possibility. Second, when we have to weld the thick sections components, then we need to use the filler metal. Okay, or if we have to, or if the A and B are not compatible with each other, okay, not compatible with each other, then also we need to bring in the third material in between the A and B, so that reasonably good weld joints can be made. So this is the case where the autogeneous welding mostly epitaxial solidification takes place, but in case when the filler metal of the different composition is used, then typical nucleation and the growth approach of the solidification occurs for the development of joint. This is about the fusion welding. Okay. But the weld joints can also be developed like through the controlled plastic deformation at the interface, okay, through the like explosive welding, through the ultrasonic welding, or through the friction welding. Okay. So in those approaches, again the metallurgical joint is developed, but through the controlled plastic deformation coupled with the diffusion. Okay. This deformation can be there at a micro or macro level. For developing the joint by the plastic deformation approach in solid state joining, like what we need, material must show some ability to get deformed. So, it should have percentage elongation, ductility in terms of say percentage elongation, or it is preferred if it is having the low yield strength. So, this is about the case. So, for causing the plastic deformation, certainly we need to apply pressure or stresses. Okay. But for realizing the fusion, we need to apply heat. Sometimes in certain welding processes, both heat and pressure are used. Okay. So, like in a spot welding. So, in a spot welding, interfacial heat is generated at the interface through the electrical resistance heating. So, this molten metal is created and which solidifies under pressure only. Okay. So, in certain processes our heat and pressure both are used. So, we can see if the section is thin or the same base metal or the compatible with base metal is to be used, then autogeneous welding, no filler metal. or the filler metal is used when the section thickness is more, but or we do not have the compatibility between the metals to be joined. So, this is the complete overview of the conditions where heat, pressure or the filler is used. So, this is one the typical case when say we are using the filler metal to join the two components say A and B. In that case, the filler metal being used for developing the joint, okay, that can be of our choice. It can be of the low strength of or of a specific characteristics as per the need, or it can be high strength, high toughness, high of any desired characteristics that we need. So, the welding processes which are performed with the use of filler, that allows the significant change and control over the properties of the weld metal. Okay. Because base metal is a part of the design, but there are many changes which occurs in the zone in vicinity of the weld metal. So, that we get the heat affected zone. So, the changes in properties which are occurring in the heat affected zone are beyond the control. Okay. So, the degradation in properties occurring in heat affected zone is considered to be very harmful, because this cannot be eliminated in fusion welding, this can be minimized certainly. So, the best part of using the filler metal in fusion welding like is bring the metal as per the requirement of the properties, say A and B, if they are compatible then we will be using the matching filler or filler which satisfies the requirement. Okay. If you want to reduce the residual stresses, we will be using the low strength filler. Like in cast iron, we use the nickel fillers or austenitic stainless steel fillers. So, but in case of the autogeneous welding, what we have to do, the two components section thickness is less and we just simply apply heat with the help of suitable heat source. So, heat source like say it can be TIG, it can be the laser or electron beam. Okay. So, we have to just supply the heat source so that the fusion of the feng surfaces takes place, followed by the solidification, that in turn will be leading to the development of joint. But certainly this will not be preferred if the compatibility between the components to be joined is not good, or if the section thickness is high, then we need require high intensity, high energy, high power density welding processes to ensure the through thickness penetration. Okay. Now, we will see what is the role of the heat in joining, whether it is fusion or it is solid state. So, what is the role that is played by the heat when it is supplied for development of the joint? So, like say this is the component, and when we apply heat from the external heat source, so the zone and feng surfaces, the feng surfaces as well as the zone which is being heated, that will be experiencing the thermal decomposition of the constituents components which are present in the area which is being heated. It may be form of like say the moisture, if it is present then moisture will be eliminated. If the hydrocarbons in form of oil, paint etc., they are present, then they will be thermally decomposed, and many times few oxides also decompose. Okay. So, when the heat is applied, the first thing that happens is the cleaning. Okay. So, cleaning will be happening like removal of the moisture which is present by vaporizing the water, the moisture which is present. Then thermal decomposition also takes place of certain oxides that help in self cleaning, and that and breaking of the oxide. So, the one aspect that is related with the welding with the application of heat for joining is realization of cleaning. Okay. Then melting of feng surfaces. Certainly for fusion welding this is an important thing, like the component to be welded, when the heat is applied we expect that the feng surfaces are brought to the molten state, followed by the solidification leading to the development of joint. But this will be happening after the cleaning phase. Okay. Then so, but this cleaning is especially good for removing the moisture or certain metals and their oxides, good for certain metals where their oxides get decomposed thermally and get removed, or they tend to get agglomerate. Okay. Then deformation, like if the solid state joining process is being used like say this, and we know that if the metals A and B to be joined are of the high yield strength and the low ductility. Okay, if this low percentage elongation, if this is the case, then the solid state joining will be difficult. So it will be better if we supply the suitable heat, either it is generated under in situ conditions or it is supplied from outside. Then application of the heat from outside, that will be increasing the temperature. Okay, this increase in temperature will simply be reducing the yield strength of the metal, like this temperature increased and the yield strength gets reduced, while the ductility is enhanced. So, the percentage elongation improves. So, this combination of change in properties like reduction in yield strength and increase in ductility with the increase of temperature when the heat is supplied, that helps in easy and controlled plastic deformation at the interfaces for development of the joint. Okay. So, like in even in ultrasonic welding or explosive welding, little heat is generated and that helps in softening and plastic deformation. Okay. So, the deformation, you see, this heat is generated, deformation is realized certainly at the interface. This can be at micro level or macro level. Okay. So, the lowering, so when the heat is applied, it helps in lowering the yield strength and increasing the ductility. Another thing that is the diffusion is another very important aspect in development of the sound, the weld joint. So, whether it is fusion welding or solid state joining, in all those cases there will certainly be the movement of atoms across the interface. Okay. So that movement will be realized through the diffusion. Higher the temperature, greater will be the diffusion, easier will be the greater will be the tendency of formation of the good sound joint. This is especially true for the solid state joining, because in case of the fusion joining, during the solidification certainly there will be first liquid to solid state phase transformation, and then lot of solid state phase transformations or solid state transformations will be occurring, and they will be involving the diffusion. Okay. So, as long as the temperature of the joint being developed is high, the diffusion of the atoms across the interface or in the weld zone, that will be occurring, that will be leading to the development of the suitable microstructure and the development of the sound joint. So, the diffusion is important, and more important it is in case of the solid state joining. Okay, because there we try to develop the joint in solid state without melting. Heat can be developed. So, as I have said, in condensed manner, heat is used for cleaning, melting, softening and the diffusion. This heat can be generated by the various approaches like chemical reactions, where acetylene is burned, acetylene and oxygen mixture is burned to produce the heat, plus other the byproducts. Okay, like heat plus the vapors. Similarly, electrical resistance heating I square RT principle is used for development of the heat, like in resistance welding processes. In frictional heating, like the heat is generated through the friction at the interface. Electric arc heating, where IR, okay, VI is used, like the arc voltage V and the welding current I. So, product of these two gives us the heat being generated. Then the radiation using the laser or electron beam heat is generated, and then interfacial friction or the impact. See, interfacial friction like in ultrasonic welding, or the impact like in explosive welding. So, all the amount of heat generated is very less under these conditions, but still there will be some heat generation, and that will facilitate the development of the joint. Pressure, when the pressure is particularly used, whether a pressure is used mostly in the solid state joining, or it is like the joining process like resistance welding processes. Okay. So, in these processes, when the pressure is used, what are the different roles performed by the pressure when it is used during the solid state joining or during the resistance welding process. So, here it helps in disrupting the absorbed gases, like say this is one component and this is the another component. So, say the two components can be rubbed, can be kept under pressure, and when, so since all surfaces will have some kind of the absorbed gases, some kind of the compounds formed at the surface. So, these absorbed gas layer is disrupted by the controlled surface layer plastic deformation when the pressure is applied. So, the gas layer is disrupted basically, and that disruption helps in bringing the metal to two metals in very close contact with each other, and that in turn helps in increasing the metal to metal contact to facilitate the diffusion across the interface and to develop the joint in the solid state. Okay. Then the fracturing the oxide layers, say here we have the two components and the pressure is being applied. So, controlled plastic deformation at the surface layers will be taking place. So, if we at the surface we have the oxide layers which are hard and brittle. Okay. So, the controlled plastic deformation at the surface under the pressure, that will be causing the fracture of these oxide layers, and once this happens, then the metal to metal contact is enhanced, and that is in turn helps in development of the sound weld joint, and this is typically observed in case of the magnetic pulse welding, ultrasonic welding, or even in explosive welding. Okay. As I said, the application of the pressure helps in surface cleaning by squeezing out the impurities. Like say in flash welding, you see the say one end is fixed, say this is a fixed end, another end is movable. Okay. So, the flow of heavy current across the interface causes lot of flashes. Okay. These are tiny unstable arcs. Okay. And this will be causing the little melting of the surface layers, and when the pressure is applied, all these impurities are squeezed out from the interface, resulting in the perfect metal to metal contact between the two components, followed by softening. So, application of the pressure will be leading to the controlled plastic deformation at the interface and development of the joint like this. So, the joint interface becomes like this at the like this. So, this is the interface zone, but for this to have the defect free interface, it is necessary that all impurities from the interface are removed, and so that kind of the removal happens especially in case of the flash butt welding, where surfaces get cleaned, by removal of the impurities present at the surface. Then solidification under the pressure, as I have already said, like in the lap welding, the current is supplied, very high current is supplied. So, generation of the maximum heat at the interface will be leading to the development of the molten metal. Okay. This molten metal under pressure has to solidify, and the solidification under pressure helps in developing the sound joint actually. And so, this is typically observed in case of the spot welding. Pressure is certainly used extensively in solid state joining for realizing the controlled plastic deformation, like interfacial plastic deformation, for improving the metallic intimacy, like say whether it is the diffusion bonding, okay, what we want, perfect metal to metal contact, or the ultrasonic welding. There also the lateral movement in case of the metallic joining helps in removing the impurities, generating the frictional heat, and causing the controlled plastic deformation at the interface. Plastic deformation, the pressure is also used for causing or realizing the controlled bulk metal deformation, like in the friction welding or friction stir welding. So, that significant plastic deformation, even in forge welding also, this the macro scale plastic deformation is involved, and that in turn helps in developing the metallic continuity. So, as I said, the role of the filler metal is there in case of joining of thick metals, where a groove is to be prepared for joining of the thick metallic components, and then this groove is filled by using the suitable filler. Okay. So, for filling the groove or gap, actually the filler metal is used, and then in certain cases like in the brazing and soldering, so what we do, the two components to be joined, a close controlled gap is maintained, then we use the suitable filler in form of brazing or soldering material. Things are heated, so this gets melted actually, and by capillary action it distributes at the interface. So, surface interaction, so the filler metal in case of brazing and soldering interacts with the base metal. Okay. There is no fusion or the melting of the fine surfaces of the base metal, only filler metal melts and leading to the development of the certain interfacial compounds at the interfaces, that in turn helps in development of the reasonably good joint. Okay. Achieving the desired properties, so corrosion resistance, thermal expansion, thermal strength, strength, and the residual stresses. These are various scenarios. Okay, so if the two components are welded directly with the application of the heat, there is a possibility that the three different zones being formed: base metal, heat affected zone, and the weld zone. All three have the different microstructure, different mechanical properties. So this kind of the joint can show significant corrosion, significant drop in corrosion resistance. So now if for certain applications, if you want that no weld joint must be, or the weld metal must be very good, must show good resistance to the corrosion. So what we will be doing? We will be choosing this such kind of the filler metal, so that the weld is made of the corrosion resistant material. So this is what we can say as selecting the filler in such a way that we can realize that desired property. Say here in this case, the desired corrosion resistance. Another possible case is like the two different metals being welded. One thermal expansion coefficient is 10 units, another is 18, say or 12, say for mild steel and for the austenitic stainless steel. If the two are to be welded, so large difference in thermal expansion coefficient will be causing a lot of issues in terms of residual stresses, distortion tendency. So what we try to do is we try to fill the gap between the two for by the fusion welding, using the filler which is having the thermal expansion coefficient of the intermediate value, say 15. Thermal expansion filler metal is selected in such a way that it acts as a bridge between the two metals to be joined. This also helps in reducing the residual stresses. Okay. Then we can also, like, strength is another aspect, like filler metal can be selected both or in all three types. So with respect to the strength, filler metal can be of the overmatching. Means, say if the base metal strength is 400 MPa, we can choose the filler metal of the 600 MPa. This will be the overmatching situation, or the matching one, where the filler metal is having the strength of similar to that of, like, say 410 or 390. So, this is almost matching strength of the filler metal, or under matching, where the strength of the filler is significantly lower than that of a. So, but each will have its own purpose actually. Sometimes the under matching filler metal is intentionally used in order to reduce the distortion tendency and residual stresses, especially due to the low strength of the filler metal. Okay. So, this is wherever we have the any special problem related with the cracking tendency, embrittlement, or the distortion and the residual stresses related issues, we try to prefer the use of the low strength the filler or under matching filler metals. So as per need of the strength or as per the need of the situation, we can use the suitable filler for development of the joint. Okay. Sometimes the filler metal is selected in such a way that it does not promote the cracking tendency. For example, the parent metal A is having the solidification temperature range of the 100 degree centigrade for a given composition. So, this solidification temperature range is very wide, which will promote during the welding center line cracking or solidification cracking. So, if the solidification cracking tendency is high, then despite of development of joint, despite of all efforts, the joint gets cracked. Okay. So, in this case we try to use the filler in such a way. So, this will be the case when the autogeneous welding is used. So, if we try to use the filler in such a way that the solidification temperature, the composition of the weld metal is adjusted, so that our solidification temperature range is kept, say, below 40 degrees centigrade. So, lower the solidification temperature range, lesser the solidification cracking tendency. So, basically solidification temperature range is the function of the heavily depend on the composition. So, if the composition is adjusted such that solidification temperature range is reduced, then our solidification cracking tendency will be reduced. So, sometimes the filler metal is selected in such a way that the STR, solidification temperature range, is reduced in order to avoid the cracking tendency of the weld joint. Okay. So, the heat input for the, say, whether it is the solid state welding or the fusion welding, heat input must be optimum. Okay. What is the meaning of this? Like if in fusion welding, if heat input is less, means whatever heat is to be, should be there is not being used. So that will be causing the development of the defective welds, like it will not be leading to the through thickness penetration, and so there will be unwelded section that will be left. So this will be the defect, like lack of penetration. This is the one very common issue, like if the heat is not proper, then it will be promoting the lot of defects in the weld joint. Okay. Or if the heat being used is too much, in that case what will be happening is, like the two components being welded and using the excessive heat, if then not just the weld zone will be very wide, but also the heat affected zone, the kind of thermal degradation that will be happening to the parent metal, that also will increase, and therefore HZ properties are very badly compromised. Okay. Therefore, so lower heat input will promote the weld discontinuities, while higher heat input will be promoted. So this is like in x axis we have the higher, this is x axis showing the heat input, and y axis is showing the weld joint characteristics. So in x axis, so when the heat input is very less, there is huge tendency of the weld defect formation, and with the increase of heat input the defects get reduced, so that in turn will be increasing the joint performance. Okay. For an optimum amount of heat, the joint performance will be the best one. Thereafter, further increasing the heat input, the joint performance will start degrading, and this degradation helps due to the excessive heat input leading to the poor mechanical microstructure and mechanical properties, coupled with the higher residual stresses. Okay. So that therefore neither very less heat input, not very high heat input will be good enough, but we need to supply the optimum amount of heat for the best performance of the weld joint. Say for in case of the arc welding, Vi is the heat being generated and S is the speed at which the arc is moving, that will give us the net heat input. So, we have the two things in our hand, either regulate the current or regulate the speed in such a way that our heat input is in the optimum range. Okay. So, this say for example, TIG welding can offer the heat input in the range of say 0.5 kilojoule per mm to the 1.5 kilojoule per mm. So, this, so for a given, for optimum condition, if it is a 0.8 kilojoule per mm, then we need to adjust the voltage, current and the welding speed such that we get this kind of the heat input. Otherwise, our joint performance will be reduced. Okay. Then like say this is the typical schematic showing the joint, which is joint with the different zones, the base metal, and when the heat is supplied, so maximum heat will be there in the zone where the melting will take place and followed by solidification, that will be producing the weld metal. A neighboring zone which is getting affected due to the application of heat, experiencing the change in microstructure and mechanical property, that will be termed as the heat affected zone. Okay. So, when a weld joint is developed, what we will see, weld joint is developed like say the component A and B being welded. So, a weld joint is there in between, and both sides we have the heat affected zone. So, this joint will fail from which location and how it can fail. So, there are certain ways through which joint can fail. One is when the deformation being experienced under the service condition is beyond the elastic deformation, beyond the acceptable elastic deformation, or when the component goes or deforms beyond the plastic deformation limit, beyond the acceptable plastic deformation limit, or when it gets separated or fractured. So, these are three different ways by which a typical weld joint can fail. Elastic deformation means the joint is experiencing the elastic deformation beyond the acceptable limit, or the joint is experiencing the plastic deformation beyond the acceptable limit, or the complete fracture can take place. So, this is one criteria based on which joints can fail. So, the different parameters will be used for designing the weld joint suitably. Okay. But this will indicate which zone is weak, like say when the load is applied. So, it may show that this the localized plastic deformation of the component A instead of heat affected zone, weld zone, another heat affected zone and B. What it shows that this metal A is weak, and therefore, and that is why only this is getting affected, very adversely affected due to the externally applied load, or this is getting fractured. So, the fracture location basically indicates, or the failure location indicates the area or the location on which we need to give the attention for improving the joint performance. For example, if instead of plastic deformation from the base metal, if it is occurring from the heat affected zone or from the weld zone, then we need to focus accordingly to see whether we need to change the filler metal, or we need to do some kind of the post weld heat treatment, or we have to do something else for reducing the adverse effect of the welding on the base metal. So, basically the fracture location or the failure location indicates the area where we should give focus for improving the joint performance. So, now I will summarize this presentation. In this presentation, basically I have talked about the role of the heat, the pressure and the filler metal in development of the sound weld joint, and when a weld joint is developed, how we can identify the location where we should focus for improving the joint performance. Thank you for your attention.